So, acids and bases. Acids and to a lesser extent bases are classes of chemical compounds which we are familiar with. And so that's about the first thing you ever do in the way of science is, you do things with lemon juice and you dissolve things and with lemon juice maybe, or you make cabbage juice indicators and that sort of thing. So little wee kids do acid-base chemistry, even if they don't know what it is. And so we know that vinegar is acidic, we know that lemons are acidic, we know that battery acid is acidic. We know maybe that drain cleaner is basic. Bases are a lot less common. Well, they're not as readily recognised. There's lots of bases out there, but they're a lot less common. So what we want to do first off is we want to try and define in a chemical sense what an acid is and what a base is, right? Rather than just saying an acid is acidic, we want to say what does that mean? And then, of course, we're going to try and quantify that later on. So, it turns out that there's various different ways to sort of define what an acid and a base is. And the one that we tend to focus on mostly, certainly in the context of what we would normally call acid-base chemistry, is this thing called a Bronsted-Lowry acid-base definition. And so one of these guys is Mr. Bronsted, and one of them is Mr. Lowry. The pictures are very dark. I'm sorry about that. I don't know why. It's because I am using this thing. So this is back about 100 years ago, and they came up with a definition, and the definition is based on the way that these compounds, which we call acids and bases, do their chemical reactions. And so they defined it like this. They said that an acid is a proton donor, and when we say proton, we mean H plus ions, right? And then they said that a base is a proton acceptor. And we use the word proton when we mean H plus because when you think about it, if you think about a hydrogen atom, right back to Monday last week, a hydrogen atom has got an atomic number of 1, so it has 1 proton in the nucleus and it has 1 electron around the outside, yeah? But if it's H plus, that means you've taken that electron off, and so all you're left with is the nucleus. And the nucleus just contains a proton. So all that really is just a bare nucleus, an H plus ion. And so that's why we call it a proton. The sort of words are interchangeable. So an acid is a proton donor, a base is a proton acceptor. And so if we consider a simple example of an acid-base reaction like this, here's HCl. HCl is hydrochloric acid. It's the acid that's in your stomach and stuff, so it's kind of one of these common acids. HCl plus water gives Cl minus, chloride ions, and H3O plus, which is something called a hydronium ion. Now if we draw these formulas out in a bit more detail, we can kind of see how this works. So the HCl has got an H attached to a chlorine, and the water's just got an oxygen with 2 hydrogens on it. And what happens in the course of our acid-base reaction is that this H, which I've labelled in red here, which starts off being attached to the chlorine, comes off and becomes attached to the oxygen of the water molecule. Right? So this H is transferred, if you like, from the chlorine to the water. And it's transferred as H+, so that means that the HCl, which starts off being a neutral molecule, if it loses an H+, what you're left with is the chlorine and a minus charge, right? So we think about the HCl initially being H+ and Cl- attached together. You take the H+ off, you're left with a Cl- behind. So that's got a negative charge. The H2O starts off being a neutral molecule. If we add an H+ to that, then we end up making something that overall has a positive charge. Yeah? So we can see that in the course of this reaction, the HCl molecule donates its proton, its H+ ion, to the water molecule, and the water molecule accepts that H+ ion from the HCl molecule. And so we would call the HCl an acid, and we would call the water a base. The HCl is an acid because in this reaction it donates a proton to something else. The water molecule is a base because in this reaction it accepts a proton from something else. So here's our reaction again. Now another little bit of definition. We can further call the chloride anion, which is what's left after the acid donates its proton, we give it a name, we call it the conjugate base. So we start with an HCl molecule, which is an acid. When it's donated its proton to something else, the bit that's left behind is called the conjugate base. And in the same way, the H3O plus cation, or the hydronium ion, which is what is left after the base accepts its proton, is called the conjugate acid. And so we can talk, for any acid-base reaction that we might write down, we can define what we call conjugate acid-base pairs. Right? So these are two molecules which are related to each other in that their formulas are only different by an H plus ion. So if you like HCl and Cl minus, H2O and H3O plus, these would be conjugate acid-base pairs. And so in our equation up here, those would be them there. Right? The HCl and the Cl minus, HCl is an acid, Cl minus is a conjugate base, and then H2O and H3O plus, where the H2O is a base, and the H3O plus is the conjugate acid. Okay, we're happy with this idea? So if you want to work out whether two molecules we give you are a conjugate acid-base pair, you're looking to see whether the formulas are the same except for an H plus between the two of them. If it's more different than that, then they're not a conjugate acid-base pair, it's something else. Okay. So we can further define acids and bases as being either strong or weak. And so initially we'll focus on strong acids and strong bases because they're easier, and then later on we're going to talk about weak acids and weak bases. It turns out that strong acids are relatively uncommon, and there's really only about 4 or 5 that you're likely to come across. There are some things called superacids, but they're kind of different again, and we're not going to talk about superacids. But your standard strong acids are going to be hydrochloric acid, hydrobromic acid, HBr, you might not have come across that one so much, nitric acid, HNO3, and sulfuric acid, H2SO4. And you probably don't have to go home and memorize those. There is going to be a time when you're going to be able to need to recognize a strong acid from a weak acid, but there's a way of doing that, which we'll talk about later this morning, which is a way of working out whether something's a weak acid or not. And so that way of working that out will help you work out if it's a strong acid, right? So we'll come back to this. And so there's these 4, but in reality, you're only, except for the occasional case where for good reasons we talk about nitric acid, it's probably going to be hydrochloric acid that we're going to talk about, right? Okay, so a strong acid, how do we define a strong acid? A strong acid is one which, when you put it in water, completely donates its protons to water molecules. Okay, so we can write a reaction like this. HCl plus H2O gives Cl minus and H3O plus. That's the one we've just seen. But we would write that with an arrow, a one-way arrow, reactants to products, right? So we would say that that reaction goes to completion. And so what that means, even though we do quite often write this, we'll write HCl aqueous. In reality, if you see that, what that's telling you is that you've got a solution that actually has no HCl molecules in it at all. Right? What it is HCl, which is a gas, which has been put into water to give chloride ions and H3O plus ions. So HCl aqueous kind of is a bit funny because there's actually no HCl in that solution at all. It's all reacted with the water molecules to give chloride ions and H3O plus. Okay? So we call it a strong acid because this reaction goes to completion. And then it just says there, note the 1:1 to 1:1 mole ratio. This is one of the reasons why we tend to use hydrochloric rather than sulfuric acid, is that a lot of the questions we get you to work through in this acid-base chemistry requires obviously that you're happy with the balanced equations and you've got that balancing, that stoichiometry sorted. But we tend to just make it simple ones like this, so then you can focus on some of the other harder stuff. So it's almost always 1:1 to 1:1 for acid-base calculations. Right? Right. So what this means is that when we perform a reaction with an HCl aqueous acid solution, right? So if you've got a bottle in the lab that says HCl aqueous, what that means, like I say, is that there's actually no HCl molecules in that bottle at all, because all the HCl molecules have reacted with water molecules, donated their protons to the water molecules to give Cl- and H3O+. So the actual molecule that can then donate its proton to something else and behave like an acid is the H3O+, the hydronium ion. Right? So if you have a bottle of 2 moles per litre hydrochloric acid in the lab, and then for some reason you decide to pour it all over your hand, the thing which is going to make your hand go all red and blistered and sore is not HCl molecules. It's H3O+ molecules in that solution. Yeah? They're the things which are being the acid and doing the acid-base chemistry. Sometimes you can have acids that donate 2 protons. So H2SO4 would be an example of this. So we can write 2 equations for H2SO4 reacting with water. In the first case, the H2SO4 will donate a proton to water and you'll get an H3O+, right, the protonated water molecule. And you'll get HSO4-, which will be the conjugate base of the H2SO4. But that HSO4- ion can also be like an acid and donate a proton to a second water molecule to give SO4-, sulfate, and another lot of H3O+. And so we call these sorts of acids diprotic acids because they have 2 protons that they can donate. And you can get triprotic acids as well. Phosphoric acid would be an example of a triprotic. But like I say, these ones tend to get a bit more complicated because the stoichiometry isn't 1:1 to 1:1 necessarily. And so we don't tend to ask you about these ones nearly so much, right? We focus on keeping it simple and then worry about other stuff. Okay, so that's strong acids. Strong bases, pretty much the only ones you're likely to come across is sodium hydroxide. Oh, hello. No, not yet.
You think if you just said an H3O plus H is minus?
Yes, you would, and yet, no, not yet. We're going to get to that, but not yet. So strong bases, I suppose the most common ones would be caustic soda or sodium hydroxide or potassium hydroxide. Both of these things you could, well, like hydrochloric acid, to be fair, you can go and buy at Mitre 10 and stuff if you want. They're some of the nastiest chemicals you would come across in first year labs, and you can buy them at Mitre 10 by the litre, and it's apparently okay. We would define a strong base as one which, when you put it in water, will completely dissociate to give hydroxide ions and sodium or potassium ions, depending on which one you're starting with, right? So strong bases are a little bit different to strong acids in that strong bases don't react with the water. They just dissolve in the water, just like a normal ionic compound that we met last week, right? So we could write NaOH as a solid, probably should have an S there, goes to Na plus aqueous plus OH minus aqueous. And again, that's a one-way arrow because that reaction goes to completion. And so at the end of the day, what we have is we have strong acids where if you have a certain amount of a strong acid and you put it in water, then you get that same amount of H3O plus ions in your solution. And if you have a strong base, then if you add a certain amount of strong base to water, you get that same amount of hydroxide ions in that solution. Yeah? So the acid-base chemistry is all about hydronium ions, H3O plus ions, and hydroxide ions. Regardless of what you start with, once you put them into your aqueous solution, that's what you end up with, H3O plus or OH minus. And those are the things that do the stuff, that do the acid-base chemistry. Yeah? Okay, so I've just said this. So again, for strong bases, this reaction goes to completion, and so does the OH minus ions, which act as the proton acceptors in reactions. Okay, so again, if you pour concentrated caustic soda on yourself and it starts doing weird things, if it's acid-base chemistry, then it's the OH minus which is acting as the base, not sodium hydroxide molecules. Yeah? Right then, so we can say that if we take some HCl and we put it in water, we get a solution which is acidic because it's got H3O plus ions in it. But again, because we want to be scientists, we want to be able to quantify everything and put numbers on it. So, how do we measure how acidic a solution is? Well, we do it by measuring the concentration of the H3O plus ions in your solution. And so this is the sort of thing we'll give you. We'll say, let's imagine we have a 0.100 moles per litre solution of HCl. Now we will say that all the time at you. And what we need you to remember is that even though we say it's a solution of HCl, in fact there's no HCl molecules in there. Yeah? Like we've just been saying. Because the HCl molecules will all react completely with the water to make H3O plus and Cl minus ions. So the concentration of HCl is 0. And the concentration of H3O plus will be the same as what we tell you the concentration of the HCl is, because of that 1-to-1 to 1-to-1 balancing that you always get in these. Okay? So if we start by telling you that you've got 0.100 moles per litre of this stuff, and this reaction goes to completion, then the 1-to-1 to 1-to-1 balancing tells you that 0.1 moles per litre of this will give you 0.1 moles per litre of this, and 0.1 moles per litre of this. Yeah? So when the reaction's finished, there's none of this left, and all of it's been turned into this and this. And so if we tell you that it's 0.1 moles per litre HCl, then you can hopefully immediately go, well, that means that the concentration of the hydronium ions, the H3O plus, is 0.100 moles per litre. Yeah? But what we do when we're talking specifically about acids and bases is rather than quantify the acidity of a solution by just quoting the concentration of H3O plus, we give this other number called the pH, which is just another way of saying the concentration of the hydronium ions, but it gives you that concentration in a number typically between about sort of 1 and 15, 1 and 14, which is easier to handle. We're going to come across this a lot. There's this idea that it's difficult to talk about really, really small numbers or really, really big numbers, and so we do a mathematical manipulation to make those numbers easier to deal with. And so the pH is defined as being the negative of the log of the concentration of H3O plus ions. Right? Where the log is a mathematical manipulation which, if you understand math and you understand logs, is fine, but for most of us is just going to be a button on the calculator that we need to remember to push at the right time. Yeah? The actual reason for logs is old enough now that even I only barely remember being given log tables at school. They're a way of not having to multiply and divide numbers, yeah? Is my understanding. Back in the day when you had slide rules, has anyone seen a slide rule before? The occasional person. I've seen one. My father had one. I remember seeing it. Slide rules are what you had before you had calculators, and you couldn't do multiplication and division on slide rules. This is right, yeah? So instead you added and subtracted the logs of numbers, which is the same as multiplying and dividing. So it's just a way around the little piece of technology not being able to do some stuff. But logs are also very useful for all sorts of other things as well. And you need to be able to confidently work out what the log of a number is. So you need to be able to do this stuff on your calculator successfully. And you can get it wrong. And I should point out that on your calculator there'll be a little button with LOG on it, and then right beside it there'll be another little button with an LN on it. That is a different sort of log. We're going to come to that one later on, I think. Yes, we are. We are going to do that one in bridging. Are we? Are we? No, we're not. I take that back. But you will definitely see it a lot in first semester. And so you not only need to be able to successfully use your log button, but you need to use the correct log button at the correct moment. Yeah? So, things to practice with.